everyone, welcome to this manufacturing process technology part 2 module 2. Brief recap about what we did in the module 1 of this particular course. So, we were talking about the various advanced fabrication processes which employ different forms of energy, including mechanical, thermal, chemical, electrochemical, so on and so forth. And in context of that, we had looked into some of the basic processes like Bressov jet machining, water jet machining, laser machining, electro discharge machining, electrochemical machining, so on and so forth. We also had a brief walkway for the various stages of manufacturing and how manufacturing evolved to the most complex form of the advanced manufacturing processes as on date. Let us look into a little bit details about these different forms of machining. So, mechanical machining, for example, the many types involved. One is ultrasonic machining, where there is a slurry composed of basically an aqueous solution of abrasive particles, and there is a vibrating head which will give mechanical energy to these small abrasive particles, which will actually embed on the surface because of the hammering action or because of the momentum that they possess towards the workpiece, and it creates some kind of a brittle fracture. Typically, this form of machining is very highly preferred mode when we talk about ceramic machining or glass machining or things like that. We have water jet machining, where there is a jet of water at a very high velocity, very high pressure as well, which comes out of a small nozzle, and it is mixed in terms with abrasive particles. It is loaded with abrasive particles. So, there is always a possibility of the abrasive particle being thrown upon a surface, which would again create the brittle fracture process, and that is how cutting is performed. So, these are typical examples of single action mechanical non-traditional machining processes. So, typically as you are seeing here, in the USM process, there is abrasion, there is an abrasive, and the abrasive comes from the slurry right here, which is actually in close proximity to the workpiece, and there is a vibrating head which will push. Similarly, in water jet machining, the cutting is through a jet, and there is also a fluid workpiece interface where this jet would typically strike, and this kind of machining is typically done underwater. Okay, so therefore, whatever jet emanates out with the abrasive particles loaded on goes through a layer of water before striking the workpiece. So, the machining medium is solid grains suspended in an abrasive slurry in the former, whereas in the later, that is WJM process, there is a fluid again, but it is really not a thick slurry, but a thin slurry with a fluid loaded with some garnets or abrasive particles. Okay. So, you can do the same with ice particles, replacing the abrasive particles. If it is replaced by ice particles, we call it ice jet machining. So, these are the different kinds of non-traditional mechanical machining processes. There are also thermal machining processes typically, which include EDM, that is electro discharge machining, electron beam machining, laser beam machining, plasma beam machining, and ion beam machining. So, these are all different processes where there is a interaction of a plasma, which is typically super hot with respect to the surface, the working surface, and this plasma kind of melts away part of the surface, makes a local pool, and then there is a fluid or a medium which typically carries out, particularly in these cases like the EDM cases, the particle which is dislodged. Okay. So, there is a discharge, and the discharge is typically in a medium which creates a plasma, and then the medium is typically a dielectric fluid which breaks down to give way to this plasma, and whenever there is an interaction between this plasma and the workpiece, it creates an erosion. Okay. And so, similarly in the E-beam machining again, there is a beam of electrons which is actually guided over a surface and super focused in a very narrow zone, so that the electrons traveling at a very high acceleration typically would go through a vacuum where the workpiece is placed, and without ionizing anything in its path because of the super high vacuum, this electron would actually work upon the workpiece and create a thermal erosion again on the workpiece. So, typically the electron does not really realize after it has crossed a few layers of lattices beyond which it starts to really share its momentum into the lattice, and therefore, there is a pocket which is created in a buried manner inside an EBM tool, and it results in some kind of a sudden opening of the orifice, and it creates some kind of energy transfer, and the electron is able to depreciate material or create a melt pool down within the surface of the material. Similarly, in laser beam machining, again the same what is achieved here by a electron beam is done through a laser beam. Laser, as we know, is a very strong form of energy transfer, which talks about a beam of photons which are highly coherent in nature and generated by a laser source, and these are actually thrown upon again a workpiece where there is air in between the workpiece and this laser beam, and the photons typically hit the workpiece and create a photon to phonon conversion. So, there is a sort of a lattice vibration which is created and which results in again some kind of local melting and also evaporation, because the laser power is typically very high. Okay. So, the e-beam system deploys a vacuum which is actually a shortcoming of the process, which kind of limits the workpiece size, but in case of laser you can do really this kind of a machining over a very large or a wide area surface, and that is the reason why laser is used sometimes for wide area texturing and various other applications which you can think of in thermal machining. Similar initiatives are taken by if the source changes to a plasma source or an ion beam, and for example the very common example in this area of the ion beam is the focused ion beam, where there is a gallium source and it gives you a stream of ions which would actually deposit or strike with the workpiece and create thermal erosion of the workpiece. So, you can do really very fine machining using these processes, but the means here is a sort of a thermal impact or a thermal shock to the material, which causes the material to either vaporize or melt in a very small area and thereby create erosion within the workpiece. Okay. So, there are many secondary phenomena which occur during machining, such as micro crack formation, formation of the heat affected zones, some striations, etc., because of remelting redeposition or resolidification of the melt which has been created, and therefore the surface really becomes a very critical issue, and the finish of the machining process becomes a very critical issue when we talk about such thermal sources. So, that is thermal machining. So, we have a similar kind of an alternate machining using chemical and electrochemical route. Okay. So, we talk about in this case, for example, the chemical machining process, you have some kind of an etching or an engraving action. So, there is an acid which interacts with the surface of a workpiece, and because of this interaction on a very selective manner in some selected zones, there is a local erosion of the workpiece material which results in the formation of an etch zone or a etch area. So, there is literally a dissolution of the material into the medium that is sent in, because of which there is machining taking place. So, we call that chemical machining. We also have a very interesting process called photochemical machining, where some particular materials which are also known as photoresists or photosensitive or photoactive materials are used. So, there are films and layers of these materials which are created, and then you are selectively exposing some of the regions to a beam of light which is at a certain frequency, and it creates some kind of a bond breakage in this particular material because of the high energy photons which are pumped into the system. And since the bonds are broken in one case or reformulated in another case, it really results in either a dissolution of this area if the bonds are broken, or if the bonds are strengthened, then it retains itself and the remaining area gets dissolved in a solution. So, there is an etching step after the photo exposure step in such machining, and so these kind of machining where there is a light beam being used and a chemical material being used called resist is also known as photochemical machining. Okay. So, that is how you can actually think of these chemical processes. Electrochemical, on the other hand, is based on the Faraday's principle. So, you have some electron transport going on with the chemical process, and typically these are redox chemistries where there is something which gets oxidized and some other material which gets reduced, and there is some kind of a redox couple being formulated between the two electrodes, due to which there is a driving of either the metal going away, which is known as electrochemical machining, or the metal being deposited, which is also known as electrochemical deposition. So, we can use either of these processes to really create a wide variety of machined surfaces using chemical or electrochemical means. So, there are many variants of such processes. For example, you have chemical milling, you have photochemical machining, you have photochemical blanking. all use chemical dissolution action to allow the machining allowance through ions in an etchant. Similarly, in electrochemical machining, it uses electrochemical dissolution phase to remove the machining allowance using ion transfer in an electrolytic cell. So, that is about chemical and electrochemical machining. So, let us now go into the first generation of the learning that I would really be emphasizing here, and that is about the micro nano systems and how to some extent such machining processes, as I have mentioned, work out in the case of micro nano systems. This is a very important aspect as far as the advanced machining processes go, because at least half a dozen of such processes have been borrowed from the electronic industry, and particularly those processes which are related to the fabrication of the microelectronic chips or semiconductor chips are really some of the advanced machining techniques, which or maybe they are the first generation advanced machining techniques which actually came out, and they have really served through their commercial cycle. Okay, so let us look into some systems for example, that why the micro nano systems, and then let us also look into some of the aspects of how to machine or how to fabricate such micro nano systems through a variety of photochemical or chemical steps, or even chemical deposition steps, so that you could actually realize very small micron to nanometer scale components. So, let us talk about these systems made up of very small components, micron to nanometer scale, which is actually these micro nano systems. They find a relatively high applicability to various fields, but then they especially find a lot of application in the field of life sciences, biotechnology and medicine, although it is not really limiting, because this if you look at defense, you look at aerospace, you look at cosmetics, or you look at the variety of other areas of life, you always almost about 80 to 90% of the times find systems which are very small, and they are giving a very high resolution by virtue of their low inertial mass. Okay, so it is really the very state of the art technology that we talk about when we talk about such systems. So, let us look into some certain aspects related to such systems, and I would just like to describe some examples here which talks about what these microsystems can do or what they are. Probably this you are able to recognize, almost all of you. This is actually one of the cornerstones of today's so called nano fabrication or nanotechnology. This is the atomic force microscope, or the AFM. So, this actually right here shows a cantilever tip which is actually meant for such an AFM. This may be something like about, let us say 300 to 400 nanometers thick, and if you look at this particular length right about here, this may be a few tens of microns. So, that is how small these things are. And then if I again look at the sharpness of this particular tip here, this is completely atomically sharpened. Okay, so, this is atomically sharpened tip. So, such an object is a very important tool for scanning of surfaces, where if there is a let us say some kind of a hills and valleys on the surface, and there is some surface roughness, you can merely scan this over the surface, and from the deflections that it suffers, may be able to reconstruct the surface over which it is being scanned. So, obviously there are two different modes in which this can be scanned over. There is a sort of a so the the AFM you can actually operate through two different modes, that is the touch mode or the tapping mode, and this is a very important example where you can see how microsystem plays a very critical role, because its own mass of this particular tip is so small that its own inertial effects are quite negligible. Okay. Similarly, let us look at this particular example here, which is a bulk micromachined accelerometer, which is actually sort of this image has been borrowed from Silicon Microstructures Incorporated, where we talk about a small proof mass. So, this mass right here in the center is actually a proof mass, and there are certain there are certain sort of patterned metallic structures which are actually a part of this proof mass, and this proof mass is pivoted over a small it's like, let us say, a small post with some kind of a spacing in between. So, this is actually a sort of a pit, you can say this is a pit, and this mass is being projected outside the pit. And on the base which is actually this particular area, this is the base, okay, the pit is actually what is illustrated by these vertical lines, and the inclined lines show the base. So, there are different structures which are carved on the base. For example, there is a structure which is actually an electrode like this, there is another electrode, and there is again a third and a fourth electrode in these two regions right here. So, the idea is that the proof mass is positioned in a manner with these sort of extended wings, you can say, of the proof mass, that as the proof mass twists and turns based on the overall motion of whatever system is carrying this small unit or this small chip. So, this there is a capacitive change between the post which is actually on the base, this is shown by this sort of, you can say, the post which is, or the electrode or the post which is on the base right here, demarcated or classified as 1, and the wings which are, let us say, the wings 2 and the wings 3, okay, which are actually hinged to the proof mass, and they are subjected to sort of movement with respect to this electrode 1. So, it is like a finger plate or an interdigitated capacitive unit that we are talking about, where there is a, you can say, change in this sort of the vibrating wings and the post electrode, and because of which the 4 capacitive changes at the 4 corners can be calibrated with respect to the total amount of roll or pitch or yaw, or let us say even acceleration, deceleration, so on and so forth. These values can be measured accordingly, and so you have a very good idea about such bulk micro machined accelerometers. Again, a very interesting example used in our day to day life is this DMD digital micro mirror device chip, which is manufactured by TI, Texas Instruments. So, what happens here is that there are a series of these micro plates which are, a cross section of which is shown right here. So, these plates are hinged over 2 posts, and these are all micro machined. The set of electrodes which are at the base, and the idea is that with electric field between the plate shown by these lines and the base, you can actually deflect the plate between one corner and another. Okay, so, you can actually rotate the plate by some degrees either way of about the hinged axes, and the idea is that if supposing there is a light beam which is falling on this DMD chip, you can see right here through, it passes through the RGB filter, for example, and it is passing and formulating an image on this particular DMD chip right here, and let us say there is a beam of light which gets reflected off such a plate, So, let us say this plate 1 is reflecting a beam of light. So, by twisting and turning the plate around its hinged axis, there is a possibility of either sort of focusing a ray to the focus of the the sort of aperture lens, which finally magnifying lens, which finally magnifies the image onto the screen. Or in other words, it can be deflected so much that the beam goes out of focus, and so it is no longer there in the aperture of the projection. Okay. So, in a way, by manipulating these various small chips through electric fields, you could transfer a pixel by pixel information of an image, and you could formulate an image with a dark pixel or a bright pixel, and that is how things are projected. And the lens would actually help by magnifying the particular image from a small scale as is obtained in this DMD chip all the way to the wall, which is at probably a higher version. So, there is a resolution involved of the size of, which is defined by the size of these mirrors, which is actually about how much would be really the pixel size. So, if we talk about, let us say 50 micron by 50 micron mirror, or even a little bit lesser, let us say 10 micron by 10 micron mirror. So, there is a possibility of sort of focusing the light and getting that kind of a resolution of an image. So, these are some examples from the silicon MEMS. We also have other examples. For example, this again shows a single chip accelerometer from analog device. There is a microphone. This is very interesting. So, there is a perforated plate, as you can see here, with some kind of a piezoresistive material, and so therefore, whatever acoustic waves are encountered by this perforated plate, it changes those acoustic waves into electrical signal, which can later on be amplified and sent into a speaker. So, that is how a small microphone is made out of these MEMS based structures. So, there are several such examples also in the area of medicine and biology. For example, these are set of electrodes, micro electrodes, which are it's used to do it's used to monitor the electrical activity of the brain tissue. Okay. So, electrical activity of brain tissue. There are other examples here. This is a slender electrode, a very tall electrode, which is actually a neuroprobe. It is used for sometimes treating by a method called deep electrical stimulation, DS. These are again set of neuron cells which are growing on an array of MOS transistors, and definitely the way that these cells would talk to each other in terms of its surface protein expressions would be relayed in form of a differential electrical signal between these arrays of MOS transistors. A very interesting example is this micro needle, which is several microns, several hundreds of microns tall, which is maybe about 180 microns or so tall, with the diameter of something like about close to 20 microns, and this actually mimics the mosquito needle, so that whenever it's used to inject a drug inside the skin, it does not damage or deflect the pain receptors, because of which there is a possibility of releasing drug without inflicting any pain on the particular subject. These are some biochips which are used for or made in silicon and are used for various detection purposes, like detection of maybe microorganisms to all the way to about different mammalian cells, and finding out their healthy state as opposed to unhealthy, or even like screening off harmful or virulent forms or stains of microorganism, so on and so forth. These are set of cantilever arrays again, which are made with an intention of biomolecular detection. So, the idea is that if I had a sequence of molecules which are immobilized, let us say if there is some kind of a single stranded DNA molecule which is immobilized onto these surfaces, and they bind to some other molecules which are target molecules, there is going to be some deflection because of the change of the surface energy, which is actually given by something called Stoney's equation, where the surface energy change between both surfaces of a small cantilever would result effectively in a deflection. So, such are some of the such or many other numerous examples are available, where you can use these microsystems in various walks of life, as you have seen. And so, let us now sort of go back into how you process these using the first generation microelectronic processes, and for that we would like to just point out about the different materials which are used to formulate such architecture. So, there are silicon mostly and other microelectronic materials. This is the most popularly available microelectronic material. There is glass and quartz. Wherever there is a need for optical transparency because of some signal monitoring issue, particularly in a sensor design, these are employed. There are polymers. Again, a very huge area is coming up about polymer manufacture. In fact, some of the processes associated with polymers have now attained the status of being on the roadmap for the international semiconductor technology, and it is used for again imprinting very small feature sizes. So, polymers like let us say polydimethyl siloxane or polymethyl methacrylate or Teflon, it is a very hydrophobic material, are very often used or employed for making these structures, these small structures. Then we have in fact the most recent forms of advanced machining which are in terms of the entities themselves. So, there is also a possibility of building chips or building these micro architectures by deploying some of the biological entities in such materials. So, these are sort of the different generations of materials which are used for microsystems planning or microsystems designing, and let us now look into the first material, which is silicon and the various associated processes associated with this microelectronic industry, which has been translated into formulation of the micro machined structures or features. So, silicon by and large is the most popular MEMS material because of its background, because obviously the MEMS processes or the microsystem fabrication processes started as an offshoot of the fallout of the microelectronic industry. So, some processes became obsolete in the microelectronics and they were picked up by the MEMS or the microsystems industry. So, silicon and its compounds, for example oxides, nitrides, polysilicon, can be categorized into 3 classes based on the amount of the range of order. These can be single crystalline, polycrystalline and amorphous materials. I think I had illustrated about all this when we talked about the materials or the basic properties of the engineering materials in the module 1 of the manufacturing process technology, in the part 1 of the manufacturing process technology. And as we all know that in single crystalline materials, almost all of the atoms in the crystal occupy well defined and regular positions known as lattice sites. Materials like silicon dioxide are amorphous, which means that they do not possess any long range order. And then there is a third class of materials which is polycrystalline, and these are single small crystals randomly oriented with respect to each other. In fact, almost all of you who have done my course on the first part of manufacturing technology have probably gone through all this and how crystal formation takes place, what are the kind of defects which are there in crystals, so on and so forth. Here we will be focusing on a little bit different aspect, and that is related to how the crystal structure of silicon can be really envisioned and how you can represent this, and then play around by introducing chemical machining like etching processes or even like some kind of employing some physico-chemical etching processes or only a chemical or a physical etching process through a beam, and so therefore we need to study about this crystallography and some crystal structure aspects of silicon. So, obviously as we all are aware that crystals are described by their most basic structural element, that is the unit cell, and a crystal is a regular array of such units repeated in 3 dimensions in a regular manner. And the unit cell of interest have cubic symmetry with each edge of the unit cell which is of almost the same length, and there are 3 different structures which are there. I think this we had earlier illustrated as simple cube, body centered cubic and face centered cubic. Also there is a hexagonal close packed structure which we do not need in the case of particularly describing silicon systems. So, the directions in a crystal are identified using a set of Cartesian coordinate system x, y, z, okay. And for a cubic crystal, the faces of the cell forms planes perpendicular to the axis of the coordinate system. For example, the symbol round bracket x, y, z is used to denote a particular plane that is perpendicular to the vector that points from the origin along the x, y, z direction. So, if I say that this vector right here is the 1 0 0 vector, the plane which is perpendicular to this vector would be known as 1 0 0 circular bracket plane, okay. And further, I mean all such planes together could be signified by this third bracket 1 0 0. So, therefore, all such planes of the type which are perpendicular to the direction 1 0 0 circular bracket, okay, is given by this third bracket 1 0 0, and that is how you represent the directions of a crystal. So, I think we will probably close this module here, and in the next module we will look at some of the basic processes related to the chemical photochemical etching or even photo deposition or photolithography, through which we can micro manipulate these silicon structures so that you could actually be able to create layer by layer into what is known as a microsystems or micro scale structure. Thank you as of now.